Good afternoon, everybody, and thank you for joining us with the SAIEE, the KwaZulu Natal Centre. We're presenting with determination of conductor current ratings with Dr. Rob Stevens. And we're just going to hold on a little bit. We have quite a lot of attendees today. Welcome to those that are coming from overseas and all over the country. So it's been very well supported, and I know that there are still numbers streaming in right now. My name is Richard Arschlager. I'm actually presenting on behalf of Kalichuran of the SAIEE KwaZulu Natal Centre. So he's just had some technical difficulties, and I will be acting as your moderator today. And I'm just going to give it another minute or so. I see the numbers are climbing quite high. We have about 250 people that registered for today, and we are already well over the hundreds at this moment. So it seems to be well supported, and really thank you for taking the time out to be part of this. So while we are waiting, I would like to just give you some considerations when running a webinar. I just would ask you if you can just ensure that you maximize your volume on your device. If you're having problems, you can post questions online, and I will then field those. I'll go into more detail on that later. Also, what we are going to busy broadcasting my camera live. I will show you, Rob will introduce himself shortly, and then we will shut the cameras down just to save on bandwidth. So please, yeah, there are going to be different sections of questions. We've split the presentation into 3 sections, and Rob will actually invite you to take or post questions online just to break up the presentation somewhat. So I'd encourage you to do that. The chat function reserved for the webinar organizers, so you won't be able to use the chat function. But please, just as I said, use the questions session, please. And then we will be making a recording of the presentation. And so I would recommend that you go to the SAIEE website, and you'll see there's SAIEE TV, and the YouTube channels are there, and you can get hold of this particular presentation and watch it as soon as it is uploaded under the past events and webinars section. So I would recommend you, if you do miss this or you want to share it with other people, if you in your organization or colleagues, I would encourage you to get hold of it over there. And then this is going to be a CPD validated course that you're attending. So a certificate of attendance will be issued after this webinar, and you will get a validation number if you're for EXA validation. Okay, so without further ado, you didn't come here to listen to myself. I'd like to introduce Dr. Rob Stevens. I've known Dr. Rob for a long time, from Eskom days when I was there as well. Rob, do you want to join us online on the webcam? And he holds both an MSc and MBA degrees, as well as a PhD. Welcome, Rob. Glad to have us join us today. He has recently retired from Eskom, and I'll send to Rob now. He's not really living in a life of luxurious rest at the moment. Seems to be quite sought after. And he currently holds a position of Master Specialist in the Technology Group. Well, he recently did until he recently resigned. And he was responsible for distribution and transmission technologies of all voltages, covering both AC and DC. He's a past chairman of the CIGRE Study Committee B2 on overhead lines, and has held positions in CIGRE of special reporter and working group chairman, and has authored over 100 technical papers. He was elected president of CIGRE in 2016. So Rob, welcome to this presentation, and thank you for being willing to present to us. I've seen some of what you have to present, and it's going to be incredibly exciting. So just thanks for taking the time out, and without further ado, I'd like to just hand over to you now. So
Hi, let me just get this back. Let me just switch off my webcam. You've all seen what I look like, and I own a jacket. Let me just start the presentation. I'll just put it on a laser pointer, which makes it a little bit more clear. And let me just get that back. Just close that one, get that onto a laser pointer there. Right, so basically what I'm going to do today, and I'm speaking on behalf of the SAIEE KZN Centre, of which I'm a member and was past chairman. As I'm also president of CIGRE, as was mentioned, so you'll see the slide format is what I'm using for this particular presentation. So you could look at it as a CIGRE supporting SAIEE, which we normally do. And what I'm going to do today is explain the conductor current rating. This has been a journey most probably over the last 30 years, really, and we've done a lot of development work in developing conductor current rating together within CIGRE and Eskom, and actually in conjunction with other experts around the world. And one of them is joining our webinar today from Spain, Javier, who was chairman of the working group dealing with the equations relating to determination of conductor current temperature, which is technical brochure 607. So the presentation today links quite a bit with what happens in Eskom, mainly because we had quite a challenge in getting conductor ratings, which I'll cover for you, and also that there's quite a bit of confusion around the old tables, new tables, probabilistic ratings, and so on. So this presentation, this webinar will cover those issues. So let's go back just to past practice in Eskom, and it was put into paper in 1970 in an engineering directive. And what they did there was they determined the conductor current rating by assuming severe cooling conditions, which I'll cover. And they used fairly simple formula, which were derived in 1941, to calculate the current that would result in a conductor reaching 75 degrees Celsius for normal operation and 90 degrees Celsius for emergency operation. But where they changed from the norm was that they tempered lines at 50 degrees Celsius. Whereas normally what would happen is if you calculate a current for 75 degrees C, you would template the line at 75 degrees C. But it was felt that the probability of actually reaching greater than 50 degrees C was quite remote, and therefore they felt that the current determined that with these weather conditions reach 75 degrees C could be used for a temperating temperature of 50. Temperating temperature, which I'll cover again later, is that particular temperature at which the height above ground of the conductor is in line with the relevant act. And that's what's meant by temperating temperature. So let's just have a look at what happened from Eskom status. Up to 1990, we used this Hutchins-Tuck deterministic method. And I must say it worked extremely well. We didn't have any accidents as a result of conductors getting to too high a temperature. From 1991, when we started looking at this work, as I said, it's gone on for many years, we looked at the probabilistic ratings and looking at, together with CIGRE, produced documents in 1992 and 1994 relating to that. And we used a fairly simple one-year data, and we had to do Monte Carlo simulations using Fortran mainframes. So it took a long time to actually crunch all these data to get the particular ratings. That actually lasted right up until around 2007, where we actually managed to improve the equations. We improved the data, and we added what is called the rate C, which was a contingency rating, which I'll cover that. So we had a normal, emergency, and contingency. Of course, there was far more data, and we had a lot more mathematical models and computer iterations. And we still calibrated the ratings against deterministic values. In 2019, we uprated these probabilistic values, and we added further weather data, and of course then new IEC standard conductors to give new ratings for that. So this has really been the journey within Eskom. Just to go briefly what was used by the EED 1970. It was the work done by Hutchins and Tuck, but what was determined here was a solar radiation of 1120 watts per meter squared, which is extremely high. If you go to Johannesburg, which is the highest, one of the highest solar rating because of the thinner atmosphere, you'll find you very rarely get above 1,000 watt per meter squared. The wind speed was 0.44 meters per, which is 1 mile an hour. 1 mile an hour wind. It was assumed to be perpendicular to the conductor. There was actually no cooling effect or given to an angle of attack of the wind. And the ambient temperature was considered at 40 degrees ambient temperature. Now, these are very severe cooling conditions, and that was why it was found that it was considered that the lines being at 50 degrees C, due to these severe cooling conditions, would in fact, if we put that particular current down the line, would never reach 50 degrees C. And that was what the rationale was. But they didn't quantify the probability at all. They just said it sounds pretty slim. So they calculated ratings resulting 75 and 90 for normal and emergency, and still within Eskom, and you might find in industry, you might find tables with a 75 and 90 degrees C heading, which refer to the normal and emergency ratings. And it's also important to note that before 1970, when we built the lines were built there, they used a temperature of 50. It was only many years later in the 80s that we actually started increasing the temperature of lines to 80 degrees C for transmission lines as a standard initially. This was really the equation used for forced convection or convection due to the wind. And you'll see here that they are empirical. It's an empirical formula, which makes it very difficult, in fact, to change it. If you change it to different, instead of centimeters, you want to use meters, etc. It's very difficult to change these constants. And this was the total equation of heat in to heat out. And this is your solar radiation, and this is your radiative cooling, and then this would be your part of your forced convection. And this would be your natural convection here. Sorry, natural convection. Natural convection is a cooling with no wind, with no wind speed. So let's have a look at the normal and emergency ratings. What they felt was that the actual conductor temperature will be about 70% below that calculated, to be around 25 degrees C. And for emergency, they felt no need to clear the line clearance, as emergency is in case of one line outer surface would be transient in nature, i.e. a matter of hours or days. This was not very well elaborated within the directive, but it actually served Eskom extremely well with having no incidents. And in fact, you found that under N-1 conditions with the emergency rating, you could use that rating actually for months, if you liked, without really having a fear of any contravention or unsafe condition arising. And this 70%, it may be correct, but in South Africa, we normally get a little bit higher than the 25. The 50 degree C was actually based on the British standard at the time. Because of their lower ambient conditions, it's actually found that perhaps inappropriate to apply it here, but it was found to be fairly safe. Now, the problems that I've mentioned, the wind direction was not taken into account. We used empirical models. The radial distribution temperature wasn't taken into account. That means that the difference between your core and your surface temperatures are not taken into account. Now, the sag of a conductor depends on the average temperature of the conductor. So it's a difference, the average between your surface and your core. And all the equations calculate the surface temperature. So if you're assuming a surface temperature of 100 degrees C and you work the sag on 100 degrees C, you might be incorrect, because you might find that you've got about 105 or 108 degrees C on the sag temperature, the average temperature. It depends, of course, on the current density, power input to the conductor, and also the diameter of the conductor. That also had a simple natural convection formula, which wasn't too far off, actually. And it doesn't, the biggest problem we had in Eskom, and why we had to go to probabilistic ratings, was it didn't allow for different ratings at different temperatures. So in other words, when you had you tempered it at 50 degrees C, but if you temperated the line at 60 degrees C, what rating would you use? Now, at 50 degrees C, we used a current which gave you 75 degrees C. So if you used 60 degrees C, would you then calculate a current will give you 85 degrees? We didn't know. So what we had to do was work out a risk of unsafe condition arising for the current at 50 degrees, and then see if we used that same risk and applied it at 60 degrees C, what would that current be that'll give you the same risk? And this gave rise to all the theory around the probabilistic ratings that we later used. Load profiles, again, I'll cover that in the case studies, but that again would not allow you or any different ratings for a different load profile. Let's get now onto the theory to calculate conductor temperature, and you can ask questions, put questions onto the question panel. At the end of this section, before we get onto probabilistic rating, we'll have a bit of a break to answer any questions you need. Okay, so under steady state conditions, the heat gain is equal to the heat lost. It's a thermal balance equation, and these are the input to the heat. So that's Joule heating, I squared R, magnetic heating, that's a transformer effect in a conductor, solar heating, and corona heating. Now, corona heating normally is only apparent under high humidity and high wind speed, and it's quite mild. So that was ignored. And likewise, convective cooling is the main cooling effect. Radiative cooling, also important. Evaporator cooling is so dramatic that it would actually drop your temperature of the conductor really dramatically, but you have to make sure that your whole conductor on the whole line is wetted before you can actually use this particular cooling function. And that's why this was also ignored. So we really then have PJ, PM, and PS equals PC and PR, and the PJ and PM are often combined into a single term. Just to let you know, and this can be found in CIGRE Technical Brochure 607, which is free download actually for anybody. It's over 3 years old. You can now download that, and you'll get all the equations that is referred to. Your PJ, which is your Joule heating, is equal to a factor which normally converts it from AC to DC. And this is your normal RMS current. Then you get your a factor which is the resistance as a function of temperature. So it'll increase your DC resistance as a function of temperature. And that's basically your Joule heating. The most important cooling effect is your PC, P convective. And that's what I've written here. This is the equation, and it's dependent on the surface to ambient temperature, which gives you your film temperature. And then there's a number here called the Nusselt number. And that Nusselt number, it was found, had a relationship to the Reynolds number. And these coefficients here are dependent on the conductor type and the roughness factor. That's how big your strands are on the particular conductor. The bigger the strands, the bigger the cooling effect in relation to convective cooling. So your Reynolds number, this also is a term which is a function of the film temperature. And then your Reynolds number is a function of air density, wind velocity, conductor diameter, and viscosity of the wind, which is also a function of the film temperature. So you can see that the higher the film temperature, the higher the convective cooling, and the higher the diameter of the strands, the higher your relationship between your Nusselt and Reynolds number. Therefore, the higher your Nusselt number. The most important thing here really is your velocity, and it makes a huge difference on the Reynolds number and overall on your convective cooling. So that's the important thing to note, is that if you're thinking about convective cooling, think mainly about the wind speed. Looking at solar heating, and we think here we have a lot of sun, so therefore should be a lot of solar heating. It's dependent on the diameter of the conductor, absorptivity, and emissivity. In other words, how dark or shiny is the conductor? And normally with weathered conductor, the absorptivity, emissivity tends to go to around 0.9. You can actually have particular coatings on the conductor so that they don't run so hot if you're using high temperature conductors. And these coatings, in fact, can give you an emissivity very high and absorptivity very low, so that your conductor doesn't get too hot. The issue with the coatings, of course, is whether it'll stay on the conductor, and then if you get pollution over the coating, whether it affects your absorptivity and emissivity, so that they both go to 0.9, and then you lose the benefit of the coating. So the solar radiation is also, so this is a diameter, absorptivity, what's that conductor look like, and then your solar radiation, which is, you can get direct solar radiation, diffuse solar radiation, and global. And normally the simple equation is global solar radiation, although in the brochure 607, you'll see the direct and diffuse. Now, important to note that solar radiation has less impact if you're running your lines really hot. Say your temperating temperature is around 100 degrees C plus, which they do a lot in the US and other areas. In South Africa, we temper it around under 80. So solar radiation does have an impact. The reason we temper it down at around 80 is because you can get excursions of around 20 degrees C above your temperating temperature, which might take your conductor to 100 degrees C, which will then lead to annealing. If you temperate your conductor at 100, you might get to 120, which might increase your annealing of the particular conductor. So that is something to bear in mind. But for those conductors that are running really hot, solar radiation has almost no effect. Another point to note is the effect of magnetic heating. And this is the heating due to eddy currents in the core, which then increases the temperature of the conductor and hence your resistance ratio. And you get 3 layers. If you're looking at different layers of conductor, layers of aluminium in an ACSR conductor, this only applies to steel cord conductors. You'll find that the resistance ratio that we mentioned, that Kj, can vary. And important to note is that in a single layer conductor, and this is a hair conductor, for example, which is 100 mil, you'll find that as you start approaching a 2 amp per square mil, your effective magnetic heating starts becoming high. So you actually start getting over 12%. if you record from your theory around the skin effect as sort of like a 1.02, 1.01% effect. Now, the 3-layer is, for example, your zebra conductor will have one current going in a certain direction around the conductor, and that the first layer and third layer will be in the same direction. The middle layer is laid in the opposite direction, so it cancels out. That's why you don't get this very high increase, but you still get an increase, and this is on a 400 mil. You'll find that as you again start going over sort of a 2 amp per square mil, you start getting into the 9 to 10%, which you need to start taking into account when you start considering volt drops and stability levels and so on. When you're looking at a 2-layer conductor, that would be a wolf or bear or chickadee or whatever. Again, this is around about a 150. You can see that because the layers are cancelling each other out, you don't get a big increase. So that you don't have to worry about too much. Just something to bear in mind, because often in the smaller conductors, although you don't normally have a voltage problem way before that kind of current density, you can get lines which have a very high current density and load going down it, and your volt drop might be higher than you expect. Just looking at the power transfer due to temperature and wind, and this is an actual line, the Georgedale lines, 275 kV in Natal at the time, and temperature at 50. Just to look at the particular power transfer between 1 meter per second and 2, and it just gives you a bit more of a feeling rather than looking at amps. So here we're looking at about a 750 amp thermal rating, and at 1 meter per second, but at 2 meter per second you can get up to about 900 thermal rating before you will reach 50 degrees C. So the important thing to note here is that if you're going to shed load or have some kind of a deterministic limit, it's important sometimes to realize that if you've got a heck of a wind blowing or a storm, that your thermal rating on that particular line is most probably not even close to being reached, even though the current is well over what you would imagine it to be. But this also indicates the big difference that you can get due to going from 1 meter per second to 2 meter per second, which is not a lot. If you consider a 2 meter per second wind, it's just a breeze, really. So the difference here is quite large, and if you have a high wind, you're looking at far higher than this, sort of 3 to 5 meter per second. This is having a look at wind speed, also sort of at a zebra conductor, and looking at different meters per second. But also what is important to note is this is running at, sorry, this is not zebra conductor, this is using very high hair conductor at 4 amps per square mil. And so it's a high temperature. You can see well over 100 degrees C. And the important thing to note here is this is with 800 watt solar, the blue line, and the purple line is 0 solar. And you can see the difference here is almost 0. It's almost negligible, especially as you get up into the higher wind speeds. So the thinking there is that if you're going to run lines at high temperatures, your solar radiation doesn't play such a big part. It does have a little bit of an effect as your ambient temperature goes up, but not a great effect. Obviously, you hopefully would not run these conductors at this kind of temperature, maybe down here, but only at 3 meters per second. Now we're looking here at the use of the steady state formula. So what do you use steady state formula for? You normally determine the long-term steady state rating of conductors and determine optimum temperature term for new lines or uprating of old lines. The long-term steady state rating is really what you'd use either in a deterministic or probabilistic rate determination. So the temperature you can use for, depending on the on the particular current that you need to push down that line, and you and conduct relating to the conductor. So you could use a very small conductor at a high temperature or a large conductor at a low temperature, giving you the same thermal rating. Now they'll have different losses, so you need to look at your load profile to see the cost of the losses and whether it's worth actually doing that. Now we're getting on to the unsteady state evaluation. And this is the equation for the unsteady state, which we thankfully can simplify. And these are the mass per unit length and the power per unit length. Basically, what this does, if you recognize this is exactly the same equation. However, for the steady state, this was 0. Okay, and then we had the heat balance was heat in equals heat out. But in this case, the heat is stored in the conductor. So it's not in a steady state. So the heat in is not equal to the heat out. It's equal to a value which is equal to this, which is equal to the average function of the average temperature as a function of time. And important to note here, this is a time constant. So in other words, if you've got how quickly does this particular conductor heat up? And I won't go into too much of the details here, but depending on your specific heat and the mass of the conductor, you can and the actual input power, you can actually determine your particular time constant. Okay, so the higher the input power, shorter the time constant, and the higher the mass and specific heat, the longer the time constant. So this is really how they work, and this is the different explanations for each of the thetas. It's better explained here. So if you're going along with a current and you jump to a current I2 from a theta 1, it will jump to a particular temperature theta after a time t, and eventually it'll asymptote out to a theta max if you keep that current constant. Again, if you go down, you drop from current I1 to I2 from a theta max, which was steady state. You will then drop down to a theta in time t and a time going off there. And the 2/3 up here from that point there is equal to your time constant, which is normally given as around 20 minutes. Now, this is an actual case where we're looking at minutes with the current and temperature. And you can see, even though the current varies quite drastically over this particular time period, from 150 up to 350 amps, or from around about 150 up to 400 amps, you find that the conductor temperature doesn't vary that much. And you can see that it's actually taking some time, in fact, to react. Even if you do quite a big drop and then coming up, it sort of averages out. And that's because of the particular time constant and time store and the ability of the conductor to store heat. So the larger the conductor, the actual longer this time constant is, and the flatter this curve will be. That means that if you do suddenly hit a particular, under operation conditions, exceed the thermal rating of the conductor, you don't have to react immediately. You have got some time to actually drop the current off so that your conductor temperature doesn't actually exceed your particular thermal rating. And you can see here that on the left here is your temperature of the conductor, and our conductors are lines mainly tempered at least at 50 degrees C. You can see it's well below that. It's around about 15 to 30, which gives credence to that assumption of 25 degrees C, And this was in September in northern Natal, which is fairly warm. How do we make use of this dynamic behavior then? Well, we know a time constant around 20 minutes. It's less for smaller conductors. So if you're running air conductor, you haven't got 20 minutes. You most probably got about 8 to 10. The wind has a major effect on the conductor temperature, and it will also then drop your variation. In other words, the cooling effect of the wind would overshadow your variation in the current. So the wind is variable again within the time constant. The load is variable. So what does this allow for? It allows for real-time rating really to be determined. In other words, you can determine the particular rating of that line at any time, which is then very useful for operators, in fact, to determine whether they need to shed load or not. And real-time systems have been used and continually to be used in a lot in the US and Europe, also in Australia to some points, and so on. Just some points to remember. At high temperatures, the solar radiation has minimal effect. So in other words, you're running your lines above 100 degrees C to 130, and we might start doing that in South Africa here with the advent of high temperature conductors, especially from say wind farms or solar farms. The important thing to note then is that your high temperatures occur at night when there's low wind speed. So the wind is the most critical point, not the solar. So where you think it's hot in the day, actually due to the fact that there's normally quite a bit of turbulence in the air, you find that the temperature of the conductor is actually lower than it is at night with no solar radiation and low wind speed. So that's quite important to note. The steady state is used for deterministic ratings, certain probabilistic ratings to determine your temperature, and I'll get on to how you use to upgrade. The unsteady state you can use for real-time monitoring, and also if you're determining risks on probabilistic ratings, if you've got weather data into the minutes, in other words, 1 to 10 minutes, you can then start using probabilistic rating, using unsteady state equations to determine what you're taking into account the time constant of the particular conductor. And there I would like to give a bit of a break, and perhaps Richard can tell us a little bit if there's any questions coming in.
So, Dr. Stephen, thank you so much. And please, can you post your questions online? There was a query about whether this presentation would be available. And I did mention right at the very beginning, I'm going to repeat it, that if you go to the SAIEE website, there is a past events and webinars section, and this particular webinar will be posted there and available to download, so you can get it there. So we have got a couple of questions coming through. This is quite a technical question, Rob. I don't know if it is going to be easier for you to see it. Do you have access to the questions panel?
I don't have access to the question, no.
Okay, so let me go through this one, but I might save this one till afterwards, or we might respond to this one individually to the individual, because it is quite extensive. 3 different OEM ratings for Kingbird ACSR are given as 710 amps, deterministic 75 degrees, 773 amps, deterministic 75 degrees. Okay, I think this is quite technical. Rob, what I'm going to do is I'll just send this through to you, and you can respond to it at the next question answer section.
Sounds like it could be the 75-degree rating, as I said, is not used. We used a normal and emergency now. So, but I think we can send that through.
Okay, so basically, I think the query or question is that this creates severe confusion among young engineers and could lead to false favoring of certain manufacturers. Given the low proportional cost of conductor, specifically in the DEX environment, should there not be a standard aggregate of generating in South Africa for different conductor types?
We've got a rating per conductor. You can't aggregate the ratings across conductors because that won't give you the thermal rating for that particular conductor. But there are different ratings given by, for example, if you go to manufacturers' catalogs, you'll find that they've got a rating there, but you don't know the assumptions they're using. So I would use, particularly in Eskom, use the standard that has been agreed to or approved, and not using manufacturers' catalogs, unless you are very certain of what the ambient assumptions and what equations they're using, because that'll give you a very different rating than the one that you might be using, and you might be using it in a different area, or you might be using it in a different way that they're intending, and that would then might lead to some problems that you might not have. I don't know what would that answer the question, Richard? Anything else?
Rob, I have sent it through to your chat to see if you can pick it up there. In the meantime, a second question here from Jason Nika. Does the wind direction play a role? Well, what impact does the wind direction role, perpendicular versus lateral, etc.? How much of an
Yes,
impact is it?
it does have a role. It's a function of the sign of the angle of attack. So that depends. If it's going along the line, the angle of attack is 0. If it's perpendicular to the line, the angle of attack is 90 degrees C. And you can get down to around about 40% cooling if the wind is blowing along the line as compared to the wind blowing at 90 degrees to the line. So that is why it's quite important, in fact, especially if you're using real-time systems, to take into account the average temperature, or the temperature at the hottest point or critical sag along the line, because if your line has bends in it, you might have some part of the line where the wind is blowing perpendicular to the line, and a little bit further along you find that it's blowing along the line, and your temperature on that span's a lot higher than you would expect on the line where the wind is blowing at 90 degrees to the line. For probabilistic rating, we actually take angles into account, take the direction of the wind into account when we actually do the simulations. For deterministic rating, they normally assume a lower wind speed and then at 90 degrees C, 90 degrees to the line.
Okay, we don't have any more questions at the moment.
All right, they can come back, and then I'll commence again with the with the presentation.
Yes, perfect. Thank you.
Great. The next section that we want to cover here is probabilistic rating, which basically means taking the risk, determining the risk into account. Now, there's a difference between in determining the probabilistic rating and deterministic rating. Just to go back quickly, it's a false sense of security if you're using deterministic rating, because you're assuming some weather conditions, and then you quite quickly calculate the current, which will give you a temperature using those weather conditions. However, you are actually assuming a risk of an unsafe condition rising, or you're assuming a risk of a conductor reaching that temperature, but you don't know what that risk is. So deterministic is actually it's actually a probabilistic rating where you're operating blind. Whereas a probabilistic rating will give you the particular risk of an unsafe condition arising, from which you can then determine the current, which will give you that risk rather than a particular temperature. So although they say that the risk is 0 because they use a deterministic rating, that's absolute rubbish. You've always got a probability, but you actually don't know what it is. And in some cases, you might feel safer doing that, but it's actually not really advisable. So it would be an idea, if you are using a deterministic rating, I'll get to the SANS 10280, which is the law which says how to actually do that, so that at least you're covered if you are using a deterministic rating. just looking at this thermal rating of lines, what does it mean now, the thermal rating and the ampacity? Well, ampacity was defined by CIGRE in about 92. And it's the ampacity of a conductor is that current which will meet the design, security, and safety criteria of a particular line on which a conductor is used. Now, design could mean that it's that you don't that you don't exceed a certain annealing condition. Security could be the ability of the line, in fact, to remain intact at a particular current. Safety criteria is normally specified in one or two regulations within the Act. And this is really what is normally the main criteria that you apply, especially at lower temperating temperatures. Now, what is meant by temperating or design temperature? It's that particular temperature that the conductor, when it gets to that temperature, is at the height above ground according to the OSH Act or the regulations in your country. Now, the other question was, is the ampacity of a certain conductor constant? No, it's not. And that's due to the wind speed changing continually, ambient conditions changing. So your ampacity of the conductor is changing all the time, constantly. So you might have an ampacity or a rating down on paper, but the actual ampacity on the line is changing constantly. That doesn't mean that it's a bad thing. It just means that you need to be aware that it's not like a transformer with a 20 MVA rating that it's suddenly now going up to 40 MVA. It doesn't do that. It might change very slightly due to the temperatures, but because it's a sealed device, it can't really change its rating very much. Whereas a line can actually change its rating 2 to 3 times in a very short period of time. So this is something just to bear in mind. Now, when you're starting to look at probabilistic rating, you need to really look at the whole factor, not just the temperature, because what happens is that if the conductor goes above 50 degrees C, for example, it doesn't mean that the whole line is falling down and that you've now got such a bad sag excursion that you will cause an accident. And that has been proven because we haven't had any accidents relating to lines particular sagging due to current going down the line, and that we might have the conductor might be under sag anyway due to various issues or tower falling or insulator breaking and things like that, or irrigation pipes being lifted into the conductor. But the actual chance of having a unsafe condition arising due to the fact you might go to 52 degrees is very remote. So what we try to do is have a look and see what affects that particular thing. So we're looking at ambient conditions. That's your solar radiation, wind speed, wind direction, and so on. Conductor types, of course. Your bundle configuration. If you've got a if you've got conductors in the lee of other conductors, you do get a slightly increased cooling. But the big thing here is more that if you've got a single conductor of, say, 800 square millimeters, and you've got 2 conductors of 400 square mil each, the thermal rating of the conductors with 2x400 will be higher than that of the single 800 due to the increased surface area. Your temperature going from 50 up to 80 or 100 degrees C, a big difference in your thermal limit. Line direction, slightly. This is more for if you're doing specific studies, and this is again due to the wind direction. If you've got a predominant wind direction, say in Durban, northeast, southwest is predominant wind direction, and you're running inland, you will have a better effect than if you're running up the coast. Then the exposure of line to the public, you can understand that if a line's going over just a field, with absolutely no traffic, you've got a far less chance of having an incident with the public than if you're going to the main highway N1 to Pretoria on a busy day. The other thing that affects it, if you do get an object under the line, and you get the line is under clearance, and you get you'll still not get any flashover unless you get a surge on the line. So you need to look at the type of surge, the magnitude, and the frequency of occurrence of that particular surge. You can understand if you get a surge every day, or you get a surge once a year, your likelihood of flashover is going to vary. Then you have to look at the likelihood of all of these factors occurring simultaneously. Then you've still got the probability of flashover if the above do occur simultaneously, because it's normally, even if you say that it should flash over, you normally got a 50% chance that it will anyway. So all of these factors, in fact, come into account when you start looking at what is really your probability of an unsafe condition arising on our lines. Now, just to go back a little bit, in the past practice, if the lines exceeded a current limit, what would happen is that you would say, okay, we need to build a new line, or we need to reconduct it, or if it's under operational conditions, you would have to shed load. And in some cases, you couldn't increase the current rating if tempered at a different temperature because of the fact that in Eskom we had the 75-degree rating with a 50-degree C temperating temperature. So if it's tempered at 60, you didn't have a rating for it. So this was the issue that we had. Now we've got an opportunity to say if it exceeds the current limit, we can actually look at the probability and see, can we perhaps increase the thermal rating in different ways so that we can, in fact, remove that particular limitation on power flow. So now how do we determine the ampacity? As I said, there's two ways. Well, actually, there's a number, the deterministic and probabilistic. The deterministic, you choose the ambient conditions, as we said, 1120 watts per meter squared, 40 degrees ambient, and so on. You choose your temperating temperature. And in the past, they chose the temperature at which the line with the conductor would reach with those ambient conditions, and it was 75 degrees C, and then they tempered it at 50. Common practice around the world is you choose a temperating temperature and you choose a current which will give you that temperature. Now, the advantage is it's simple, but as I said, the disadvantage is you operate and design blind, so you don't know the risk that you're actually taking. Is 50 degrees C okay for a line in the Northern Cape or desert area where you get to about 45 degrees C? You don't know that. So the disadvantage of the deterministic is that your choice here of ambient conditions, how good is that? And how realistic is that you can say, well, if we use those ambient conditions and calculate the current, we'll be safe under all ambient conditions and all other conditions that I've mentioned. You don't know. And one of the big issues in the US was that when markets came in and they needed to increase power flow down transmission lines, they changed ambient conditions. Instead of 1 foot per meter per second wind speed, they increased it to 2 or 3 foot per second. Suddenly, they increased all their ratings on their conductors. Thermal limits were removed, and they could run the lines with the new rating. The only problem was that it increased the temperature of the conductor, and that's when it sagged into a particular tree, causing a blackout into the northeastern part of the US, which then actually led to a lot of work done in CIGRE to see what ambient conditions you should use. And now in the regulations within the US, you can't just change the ambient conditions to suit your marketing ability and to get more money for more power going down the line because you increased your wind speed. So let's look at the probabilistic approach. So the probabilistic approach really takes, as I said, the probability of a particular unsafe condition arising for a particular current. it doesn't really use factors of safety because you're bringing it into account with your determination of risk. Why use this approach? Well, basically, you know you're not operating blind, so you know what risk you are taking for different parts of the country, and you can actually use this particular risk to make sure that you don't exceed it at any time if you are going to increase the current. What are the disadvantages? Well, it takes a lot of computational power, a lot of data, a lot of analysis before you can actually determine what rating it is. You can't just do it on a spreadsheet. The advantages, you'll have the same risk for different lines in different areas with different loads and so on. So you can be certain that your risk is within a particular region, and you can also compare your risk against other risks. For example, Kuberg's probability of an unsafe condition arising is 1 × 10⁻⁶. So if you in that area, you can say, well, at least our line from a thermal rating point of view is in the same range. And in fact, in Australia, they're running it around 10⁻⁹, whereas we're running sort of 10⁻⁶. So using a probabilistic approach, you can get a higher thermal rating. In some cases, you might get a lower thermal rating, depending on the risk you're willing to take. There's more knowledge of limits. You're not operating blind. There's no guess on a factor of safety. In other words, make it 2 or 3 or have that at 1.5 or whatever. Is a consistent approach. Desert areas, same risk as forest areas. And you can have an opportunity to fine tune with a lot more variables. So now you can start using, for specific cases, you can use, for example, line direction, local weather, load profiles, and things like that. How did we determine this absolute probabilistic determination? There's different methods. What we use is called an absolute approach, where you'll get an absolute rating or probability of unsafe condition arising. This work was done in the 90s. A lot of it was done by one Eskom employee called named Johan Swan, who's now in Ireland. And basically what this is a probability of an unsafe condition arising is linked to the probability of a temperature being reached, the current being reached, which we normally consider as 1. In other words, we're saying we're going to run it flat. If it's 100 amp rating, we'll consider that the current is always at 100 amps forever. You've got a probability of an object being on the line, and what we tuned there was that we would have double-decker buses going from Joburg to Pretoria at a certain interval at 4.5 meter heights, sort of a really conservative approach. And then we took actual surges on particular lines at 2.5 per unit, and we actually modeled those to also ensure that we had a rather severe situation. As we said, the disadvantages, you need to use a lot of data, a lot of weather data, but the advantages is that now if you've got an area with, for example, that you're only reaching your current once every 5 years for an hour, you can actually bring that into account and give yourself, for the same probability of an unsafe condition arising, your probability of temperature being reached can be calculated from a far higher current. So you can actually therefore get a higher current than you otherwise would have. Now, what is another approach used is called the exceedance approach. It says, what percentage of time do we exceed our temperature? Which might seem rather crazy, because if you temperate at 50, you would assume that you never go over 50. But that's not true. You always go over, normally would always go over your temperature at some point in time. Doesn't mean the line is not safe. It just means you're going over your temperature, which means your sag might go under the clearance for a certain point in time. It doesn't mean it's not safe. It's used in England. It doesn't take everything into account, doesn't take surges, doesn't take load profiles or anything like that. The advantage is it's quite simple, so they can do the run without working on too much effort. All they do is determine the amount of time the conductor is above the temperating temperature. Also note that the temperating temperature, your lines normally only have a very few spans that are ground clearance limited. So you might only have 20% of those lines that are ground clearance limited. The rest is either weight to wind span, or they're going over valleys or something. So although you might think, gee whiz, we can't go under clearance, not the whole line. In fact, you might not go at all because of the survey buffer that they use. So again, don't think that we are going under clearance in every particular case. So the issue though is, what exceedance level should you actually use? Should you use 2%, 3%, 5%? So just to give you an example here, this is a cumulative probability of exceedance. And these were two lines, and this was one line with the exceedance measured at different points in the line. And this, you could say, is a 20% exceedance. At one stage, you could get nearly 950 amps down it. The other one, you could get to 1,050. So again, if you keep the exceedance the same, and depending where you are, you can actually vary your rating on that particular line. Now, in this case, you would have to take the lower rating to actually determine the actual rating of the line. However, just as an example to indicate that over a 100-kilometer period, you might find very different ratings for the same exceedance. Now, this is an example used in the US, in the UK, for different temperating temperatures. This was the previous determining, and this is the new one based on exceedance percentages. And they've used this now for many years with quite success. They've got summer, spring, autumn, and winter ratings. However, in South Africa, we found that due to the low wind speed and fairly high temperatures in winter, we couldn't separate. So we've got one rating for the whole year round. But what is important here is that for a single conductor, before you were rating at 610, 795, or 912, now if you're assuming a exceedance rating of 3% at 50, you can go to 745 or 989 at 75 degrees. So depending on the particular, on the needs on the network, you could have a fairly small conductor at a higher temperating temperature, or a large conductor at a lower temperating temperature. But in addition, you can see that for 10%, you might use that as emergency rating, 3% as your normal, or 0.1 as your normal. In each case, it's above your particular previously deterministic rating. Now, in this case, it was because their deterministic rating was fairly conservative. They used conservative weather conditions. This is using actual weather conditions. So in the UK, they've actually managed to increase the particular rating of the conductors by assuming a 0.1 exceedance, which was accepted within the utility and legislation. So what did we use in South Africa? We used absolute probabilistic method, extensive data. As I said, we used severe conditions for surges and frequency of surges, and we calculated probabilities and kept constant for each conductor type, so that we didn't vary the particular probabilities. Initially, we had problems in twin or single at different probabilities. However, that was resolved in time. Just looking at the data now, we've got about 147 years of data, and these are some of the spots weather data stations, and these have been increasing over time. So we've actually got more and more weather data coming in. Important as well is that not all weather data is from airports, because your wind speed at airports is generally higher than it is where the line is. So you need to actually take weather data, wind data in areas where there are a more realistic wind speed, and that was what was done. Now, when we came up with the, similar to the exceedance rating, we said, what kind of probabilistic PCT should we use? And so what we said was we would then calculate our PAC, unsafe condition arising, and we would keep it constant. So in other words, we know that what we've done at the moment is safe. We've used it since 1970, and we haven't had any problems with it. So we don't want to now say that we will reduce all the current ratings, because that we would then say, well, why do you want to reduce it if it's safe? But we don't want to increase it, because we don't want to just say, well, because it's safe, we can make it less safe. So what we said, that we'll keep it safe, we'll calculate the probability for that, and then we'd keep that the same, and we'd use that for the different temperatures. So now we've got a means whereby we've got a rating of 75 and 90 for 50 degree C template. We could then say, okay, now we've got a 60 or 70 degree C template. What is a rating? Well, we can then calculate the probability for 50 degree C, keep the same probability, calculate the rating at 60 and 70 and 80. And then we can actually optimize that temperature to make sure we get the correct current. So these are the new ratings now. We've got rate A and rate B, which is instead of the normal and emergency. And these are 1.2 in a million and 6 times 10 to the minus 6 in a million respectively, based on the 75 and 90 degree C ratings. So the new names were assigned. We called it normal and emergency rather than 75, 90. So the important thing is that although the ratings may appear different to the old ratings, they're not less safe. They're exactly the same risk that you will have. So the 60 degree C rating will be higher than the 50, and the old 75 and 90 ratings calculated for 50 degree C, but the risk is exactly the same. Now, what was also introduced, because of the thermal time constants, we introduced a contingency rating, which is allowed for only up to 15 minutes. This, as far as I know, has not been used very much. It's to allow the operators, in fact, a very short time, where if they have got a stability problem on the network, or a situation where they've got to shed load very rapidly, that they can have a little bit of time to allow that particular line to run up to the rate C, so that they can then have a bit of time to, in fact, decide what to do. And that would be up to 15 minutes. So this makes use of the assumption that large ACs have a significant time constant and generally not a big benefit. It doesn't have a big benefit on the smaller conductors because of the time constant being so short. So you won't have much benefit, but where you really got a problem on the network, which is really our bigger lines, your quad zebras, triple burst fits and triple turns, that you'll find that you need this particular ability just to hold that line in for a little bit longer, so that you can make some other arrangements, so you don't have a blackout and things like that. It's only to be used under severe conditions, not under normal, as you can understand, under normal conditions. And this is how it was determined. We tried using the probabilistic ratings and to work on the probability if it happens 1 hour per year, but we found the currents were so high that it actually just didn't make any sense. So we determined another rating, which was the time constant 1.63. We determined a current which will result in 1.63 rate B. We used that current to determine the steady state temperature of the conductor, assuming very severe ambient conditions, similar to the EED 1970. But we included a density factor of 1,500 meters, which is very conservative. And that gave us a theta max initial. Then we assume the conductor is subject to a steady state current rate B with the above, and we calculated an initial 2. So we said, okay, fine. This is the theta max that will result from this current using these conditions, which will give you your temperature at the after time. We then determined what current will give a particular, if we use rate B only with the above ambient conditions, the theta initial 2, and then we calculated a current that would raise a conductor temperature from initial 2 to theta max in 15 minutes, and that is your rate C. For larger conductors, we used 25 minutes to be a little bit more conservative, but I said that you can only use it for 15 minutes, not 25. So the larger conductors will never get to that theta max that you have determined. Just having a look here at the different ratings. This is your rate A, rate B, rate C, and these are the increases. And you can see for the larger conductors, you get a far bigger benefit due to that particular thermal inertia, because you can really pump that current in without it increasing the temperature very much. But if you're using really small conductors such as here, you've only got about a 30%. But you shouldn't really need rate C for these small conductors because you normally got a volt problem anyway. It's really used in these sort of areas where you've got a turn or zebra conductor type situation where you've got a stability problem. These are the results, and I hope you can see this. Well, it will be, this is part of the ESCOM standards, and you can see the rate A, rate B, and the rate C for the various conductors. And as I was saying, you might be able to use a fairly small conductor. Say you want a chickadee, you need 800 amps, you can use either a chickadee at 80 degrees C, or you could use a kingbird at 50 degrees C. And that'll give you the same thermal rating. So depending on your load profile and the losses on that particular line, you can then determine what you want to do. But the other thing that you can do is say, look, I need a line of a rating, my rating at, I've got chickadee at the moment at 50, at 600 amps, I need to go to 800 amps. Instead of changing the conductor like we did before, you can now increase the temperature to 80 degrees C and run it at 800 amps. And changing that temperature you can do by just increasing the tension on the line and shortening your insulator strings, or using inverted V insulator strings and things like that. So there are different ways in which you can increase the temperature without changing and increasing your rating without changing your conductor. So that's quite important. Just to touch on here, the SANS 10280, this is your conductor current rating in legislation now. So the conductor ratings can be determined either by assuming worst case conditions or by assessing risk of an unsafe condition that arises, which is your probabilistic method. In the case of deterministic ratings, the weather assumptions will be in accordance with CIGRE brochure 299. And this is what was given there. So in other words, when we said you can have 1 meter per second or 0.5 and 1120 watts or so on, a lot of research went into this, and this was the internationally agreed norm for determining deterministic rating. So if you're using a deterministic rating, use these weather conditions and you'll be quite safe. The deterministic capacity shall be performed based on equations found in thermal behavior of overhead conductors 1 and 2, and that's under CIGRE Electro 144. In the case of deterministic method, the temperature or design temperature of the line is the temperature that shall be used in calculation of the current. What we did there was we said you won't now be able to temperate the line at 50 and rate it at 70, calculate the current that'll give you 75 degrees C. Can't do that anymore. The probabilistic method is used shall be formed in accordance with the article entitled Probabilistic Determined Conductor Ratings, and is published in Electro number 164. Current ratings in different geographical area, different weather conditions shall not result in probably unsafe condition arising at is higher than the highest probability already exists in the areas. Based on current analysis, probability shall not be higher than 6 by 10 to the minus 6 for normal operating conditions. That is just to state that you can't now say, well, in this particular area, we are now going to increase the rating and we're just going to change the probability. You can't do that. So I think if you can follow the, and to say that the ESCOM tables are fully in line with this legislation. So what are the differences? Normal contingency emergency is not only 70 or 90, you've got a rate A and a rate B. Rating for conductor is not constant, depends on temperature. Lines in the same area could have different ratings. And then again, your protection settings. So if you've got a triple turn in one area, it might not be the same as rating as another because of different temperating temperatures. And these are the temperating temperatures and the effect of it. And you can see the for particular exceedance for hair conductor. Just to give you an idea, as we've shown from the table. So looking at the tables, the tables are generic for South Africa. There's an option to use different temperatures for increased power instead of a different conductor. So you can upgrade and you can optimize new lines with the optimal temperature. And it shouldn't be that we just say, no, we'll design it for 60 because we think 50 is too low. You need to actually do it objectively and say that what current do we need, what conductor can we use, and then what is the optimum temperature for that. Remember, the risk is the same. For a particular current and a particular conductor, you've got the same risk for all the temperatures for different increased currents. So the use of the exceedance method, what we've done, which I'll cover in a case study, is we use the exceedance level and load profiles, in fact, to determine an increase in rating. And this also helps you whether you need to use real-time monitoring, whether it can be used, and whether it is of use. And this is just an example of exceedance using different load profiles for the same exceedance, same line, same area. Using different load profiles, you can get a variation between 750 amps through to about 1,200 amps. And you might ask, why is there a load profile? Why does that have an effect? Well, if you've got a current pushing down the line 100% of the time, you will obviously, with any variation, get that a higher temperature than if you had that particular load going down for 1 hour a year, for example, and the rest of the line being 20% of that. So you can understand that the temperature of that particular conductor is going to vary with the current flowing down the line. And that's why the load profile does have an effect. However, in determining our tables, we assume that the current is permanently flowing down the line. And Richard, that's the end of the second slide. We can take a few questions. We are running a little bit short of time.
Okay. Thank you very much, Rob. Yes, I've got a couple of questions quickly that have come through. Okay, here's one. What is the safety factor in percentage for overloading a conductor or running beyond maximum current carrying capacity, and how long can you run a conductor beyond its thermal rating without damaging that conductor? Thanks, Nati Ndlela.
Okay, the conductor is not going to just burn off and fall on the ground. So if you're looking at the safety or the integrity of the conductor, you need to look at the annealing of the conductor. Normally, and that's with I'm talking now your standard ACSR conductors, double AC conductors, not your high temperature conductors. So if you're looking at really going anything above 100 degrees C, you will find that, for example, if you go 1 hour over 100 degrees C, and then you do it again a few months later, you've actually got a cumulative effect of 2 hours. So the effect of annealing is cumulative on the particular conductor. What that does is it means that your aluminium gets softer, and in fact the aluminium then is less supportive of the conductor. and you then find that your sag may be a lot higher than you otherwise expect. So you need to be a bit careful, but it's normally only around about 100 degrees C that you start getting those annealing. Some will argue that it's above 80, but the effect above 80 is rather minimal. CIGRE has got documents on how to calculate the annealing effect of reduction in strength of the particular conductors. So the line in that is fairly robust actually compared to a transformer or breaker or line trap or something like that. You don't really damage the particular conductor. But you need to be careful. You can't just run it, say, at 120 degrees C for a month and expect nothing to happen. It will actually anneal. With the high temperature conductors, they are resistant to that if you're using high temperature alloys. And if you're using a ACSS conductor, the strands are completely annealed. So you don't have that problem either. So you can go up to 150. Then it just depends on the steel core, which can take far higher than that. And then the only problem that you might have is your galvanizing coming off, and that's where they use mesh metal, which can go up to about 180 to 200 degrees C. So you don't have a problem with that. So the issue is just be careful. But the actual damage to the conductor it can be fairly minimal, especially if you're running temperating temperatures as we are, sort of 80 degrees C and below. I hope that answers that, Richard.
Okay, no, I think it does. There was a question as to where one could possibly get the ESCOM standard on probabilistic conductor ratings. Is it publicly available or not so?
As far as I know, it's constrained. It's a constrained limited distribution. I think it's within ESCOM only. I stand to be corrected. There might be. I know that ESCOM does share standards, but I'm not sure about this particular one. But I think the best is to contact the lines department, either Riaz Vajes or Arthur Berger, on that. I know that if you buy into it used to be into the website, you can actually get ESCOM standards, and this may be one of those that is available. I know it is available for example, substation layouts and things like that. So there is a possibility that this could be, but I don't know at this point.
Yes. Look, also, I mean, I think your understanding is that some of this probabilistic study is available in bulletins from CIGRE as well. That would possibly, it wouldn't have the exact ESCOM standards, but the probabilistic approach would be there.
On those in the SANS 10280, the references are given there. Also TB 299 and TB 607 is the one which has the particular calculation of the all the equations, how to calculate the conductor temperature for steady, dynamic, and adiabatic state.
Yes. So there was just a notice that you can subscribe to the ESCOM standards technology page from Distribution Technology. There is an access point. I know that our company does already subscribe to that. Then there was a question here on the issue of the question from Riaz Azmal. Hello, Riaz. Is the probabilistic approach more suited to areas with a smaller ambient temperature swing? In areas where you have large ambient temperature swings, would it not present a higher risk approach?
No, it doesn't. It actually, with the higher temperature swings, at least you know what your risk is. The problem with the higher temperature swings in using a deterministic approach, you have no idea what your risk is. So you are you might think you're safe, and you're getting temperatures, for example, in the deserts, you're getting over sort of 50 degrees C, but you've got no idea that you've assumed a temperature of 40 and you think you're safe. The probabilistic approach is really useful to use the actual weather data from those particular sites, so that you can actually get your rating based on the particular unsafe condition arising. For example, 6 times 1 times 10 to the minus 6. You can then calculate your current from that particular ambient condition set that you will get in those areas where you do get the high swing. So the probabilistic approach can be used anywhere. What we found was we took a fairly conservative approach to get the tables, so that the probability is very similar. It's actually most probably a lot better in a Cape Town winter than it is in a Namibian summer. But it's fairly conservative throughout. In this case study, I'll cover a little bit where we use the actual weather data from the Western region to actually increase the temperature, actually increase the rating of the line for a very short period of time.
Fantastic, thank you. I am conscious that we are running out of time. I'm going to there are a couple of comments that maybe you can address, and then I think you must go on. One of the comments here from Jan de Kok: the critical part of a line is often the line end equipment that may overheat, leading to, I think he's got your runaway. I'm assuming that's thermal runaway. And maybe you can just comment on that aspect of it.
Yeah, no, look, with this, you've got to look at a circuit rating. This is part of the circuit. No point increasing your thermal rating well up and then burn your line traps or exceed your breaker rating or transformer rating. It doesn't make sense. But what we're saying here is that you can actually remove this constraint. You'll have other constraints. You'll have a stability of voltage, terminal equipment constraint. But what we're saying here is that if you might be able to, by doing certain things, remove your thermal rating of the line constraint by either increasing temperature or whatever. So that's the last. Ignore the last point.
Just a comment from Javier Iglesias. He always wanted to reinforce the idea given by Rod. He said here, in Spain, we made a pilot project to estimate the risk using deterministic assumptions. We found that in a particular region that the wind speed was well below the assumptions of 0.6 meters per second during non-negligible periods of time. So our assumptions have a risk, as mentioned by Rob. I think you've actually just reinforced that.
Yes, what we had to do there is Javier, as I've mentioned, is the chairman of the working group that actually developed the revisions of the particular equations, and they've done a lot of work in Spain on this, and thanks, Javier, that's very valuable. Yes, it also leads to the rather use the probabilistic approach if you're using actual weather data. Because in your particular case, you might find that your 0.6 meter per second assumption is actually not really good. But what we had to do with SANS 10280 for the regulation was we had to, because a lot of perhaps municipalities or smaller utilities might not be able to do the full probabilistic approach, and they might not wish to use the Eskom ratings or not have the same conductors. We said that let's rather use a internationally recognized set of standards, which was agreed in the US and CIGRE globally. So that gives you the technical brochure 299, which does give you the 0.6. But it is a risky, and as I said, we don't know what that risk is until you do the probabilistic calculation.
Okay. So Rob, I'm not going to take any further questions at the moment. I think you can go straight through to the case study.
Thank you. All right, so now basically what we had here was, it was a 66 kV line, and it was a hair conductor and oak conductor, triple AC conductor. And what they had to do there was they needed to increase the transfer capacity for just 6 months over the winter period. And then they were putting in a new line, and we were going to build a new substation, so the current on the line would drop after that particular point in time. So it needed to be utilized above emergency limit for 20% of the time. So it's not all the time, but they needed to increase the line from 292 to 390 amps, which is quite a lot. And This was over the winter period, and we said, how can we actually do this? Because they couldn't reconductor the line, they couldn't retemplate the line, they just needed it for a very short period of time. And fortunately, it was in the period of their winter. So we determined the absolute probability levels. We did a corresponding exceedance level for a flat load profile, and then we determined the ampacity, keeping the exceedance level constant with the actual load profile and actual weather conditions. So we said, well, look, it's not going to be a flat load profile, it'll be an actual load profile, and it's not going to be the average weather conditions used around the country. We will use the weather conditions experienced at that particular time over a few years, because we didn't know what the weather was coming up at that particular, to calculate that particular exceedance level. So these were the particular risks that we looked at the time, around about 2 times 10 to the minus 6. And this was the effect of the load profile, where we had hair and oak. And this was the hair at 95% load profile, and this was your hair flat. You can see it even with a 95% makes a big difference. And this is the oak, which is the alloy conductor. So if you assume a 10% exceedance, you could increase it from around about 300 amps up to around about 400 amps, just because of the profile and the weather that we are using. And this is what we actually did, and we allowed it to go up to that particular rating. And you can see that we had one incident. Now, this is important. A jumper joint failed. Why would a jumper joint fail? A jumper joint is never under tension, and if it's not put on properly, it'll actually burn off. Normally, your midspan joints will fail long before the jumper joints because they're under tension. So if they're not built properly, they'll fail. But that's the only issue that they had. There was no other incident. The line achieved 400 amps on 4 or 5 occasions. So in other words, it wasn't being pumped at 390 plus all the time, but it did give them that little bit of leeway where they said, look, we're not increasing the risk because of the weather conditions, because of the load profile. The risk is exactly the same that we had for the steady state. However, due to the specific conditions, we can increase the current to give us that same risk. We didn't shed load, and this was right over the Kalichuran area. Had we shed load, it would have been a disaster. So we managed to deload the line after 6 months, and it saved many hours of operation in a volatile area. So the important thing to note here is that it's not permanent. It's taken for a very short period of time. They also did inspections on the line, checking the critical road crossings whenever the line went temperature, the current went up or the wind speed dropped. We've done similar cases in Natal as well, in the Kokstad area, and they again recommended that if the wind speed dropped below 1 meter per second, that they just check the critical crossings should the current be at the very high level. This 400 amps is very high for a hair conductor, which is 4 amp per square mil, which is definitely not good for any losses, and it's really high loss. So it's really for a particular in sort of non-normal event, and it needs to be handled with care, with proper analysis. You can't just assume that you can do all of this with any line at any time. So just looking then at the different methods, in the summary, there's different methods of probability. We said we had exceedance and absolute method, and then exceedance with load profiles or with actual weather being used. The absolute method can be used as a basis for exceedance to determine your actual probabilistic levels, then determining what exceedance relates to that probabilistic level, and then using weather or load profiles to actually increase it at the particular in a particular condition. Use of load profiles has a big impact, as you've seen, but you need to be very careful in application. Use to determine possible benefit of real-time monitoring. So if you put now what we found with real-time monitoring, if you've got a low temperature, your exceedance, your real-time system will tell you that your lines are going above 50 degrees C and you get zero power down the line. So real-time systems are normally very effective if you've got 80 degrees C template plus, and they're very good if you've got like 120 degrees C template temperatures, because your probability of getting over that is quite low, so you can actually get a very high current at some point. So when they come and say real-time can actually increase your rating, not always true. There was a paper I wrote in CIGRE on that, which we can send a few years back. So how do we use these? You use the approved standards for current ratings. Rate conductors depending on templating temperature, refer to normal or rate A, rate B, and not 75 and 90. Emergency refers to an unplanned outage. The rate B, this is the rate B. It's an unplanned outage. In other words, you can't take it out of maintenance and then say, I'm going to rate the other line as a rate B if you've got two lines. That's actually not what it was meant to. It was an unplanned outage. In other words, if you're taking a line out for refurbishment, you've got two lines in an area, you can't rate the existing line as rate B. It's got to stay as rate A, especially if you're doing it for a few months. So time is not given, but restoration should be as rapid as possible. Application for planners, operators, and designers for new lines. Thermal limited network with designers to obtain optimal temperature and conductor combination. This is really good if you are using a very high, very peaky profile line. You can actually use a high temperature with a small conductor, so that the capital cost is low, but you actually get your power down the line, that your power requirement that you need. You don't need to then put in a very high or really large conductor for peaky load profiles. For flat profiles such as smelters and stuff, your losses are so expensive that you normally have to go for a large conductor, but then template it down, template it at 50 degrees C, and that'll save you a cost on the line. Note that the difference in temperating in cost between 50 and 80 is not a lot. It's normally about 3 to 5% of the line cost. Now, if you've got a long line, that's still quite a lot of money, but it's not as you might think, a lot more than that, and that's because a lot of lines aren't ground clearance limited. On existing lines that are thermal limited, you can use a modified exceedance, which uses the weather and load profile. You can use real-time monitoring, as I said, though, normally above lines tempered at 80. You can increase the temperating temperature to increase your rating. You can retension it. You can use shorter insulator strings. Now, you don't reduce insulation. It's actually not really shorter. That you could use an inverted V or a Y configuration. That'll give you the same insulation capability, but with a less distance from the conductor to the tower. Or you could use higher towers, which costs you quite a bit. Or you could use you could change the conductor. Now, this is where your high temperature, low SAIEE conductors normally come in, because for the same diameter, you can actually they don't vary with the sag doesn't vary with temperature. So if you've got a certain conductor with a certain diameter, you could put a high temperature conductor in and go up to 150 degrees C, whereas before you could only go to 50. And there's two CIGRE brochures on this topic. The first one was brochure 244, which looked at different conductors for uprating of lines, and it covers all of the options relating to high temperature, low SAIEE conductors. And you need to look at the knee points and a whole lot of stuff relating to how you actually implement that. But that is something we can look at, and we've set up a work group now looking at high temperature conductors for new lines, where you would actually use those. So, methods to remove constraints. Deterministic method, don't use a deterministic method. In other words, don't increase the wind speed without doing anything, without just assuming, because you don't know the risk, and so you cannot increase the wind speed or decrease the ambient temperature or whatever without analyzing the risk. So you've actually got to go into the probabilistic method. Then the probabilistic used with care. Two methods can be used, one to increase risk, the other to retain the existing risk. In other words, you can say, I'm going to increase the risk. The risk on this line is 10 to the minus 9. I want the risk of my network is 10 to the minus 6. I want to actually increase it to 10 to the minus 6. That's very seldom used. We don't use it here. To increase risk needs to be used with care, and to retain the same risk can be used with local weather data, load profile. But what you really need to look at then is, I would recommend increase the templating temperature and then use the rating based on that new templating temperature would be the safest way for a permanent increase. I would not use any other method for a permanent increase. So limits to probability can be increases of temperature of 20 degrees C, as I've mentioned. If you do not have 10 minutes, don't use these methods on lines above 80. That's why we limit it to 80. If user conductor could anneal with a sag mode, as I've explained in answering the question. Now, if you've got annealed conductor, you don't need to worry about that. So in conclusion, the thermal rating depends on many factors, not common to other parts of substation. As I said, with the transformers, line traps, breakers, you haven't got this ability to increase the rating. So it gives opportunity to remove constraints in many different ways. You can either use probabilistic rating, real time, increasing temperature, or reconductoring. You can remove most constraints, can be reduced or removed on thermal rating. And then use of compensation of lines can assist to remove the other constraints. So if you've got a voltage limitation, use shunt capacitors on higher voltage lines, reactors, regulators on lower voltage lines, and then for stability, you can use series capacitors or alter the bundle configuration to remove those kinds of constraints. So these are just acknowledgements. This is the last slide. Eskom Line Engineering, I worked many years here with Arthur Berger and Riaz on these issues. Again, on CIGRE, the SAIEE KZN Centre, and also the SAIEE head office. Minx was very helpful in getting this webinar set up. And here is my contact details should you wish to email me for any further questions. Richard, that's it. Over to you.
Rob, thank you so much. It was quite an education. Yeah, I've been in this game for a while, but I'm just learning all the time. That's what I suppose being an engineer is about. Rob, just a question from my side quickly is CIGRE itself. I mean, how does one get involved in CIGRE to a certain extent? I see there's quite a lot of interesting work that you are doing there.
Yes, look, it's you can go onto the website. There's a local website, South African National Committee, or you could go to the international website where there's a join button. What you would do is join through the South African National Committee, and the nice thing is you can join as a company. So that means all your employees have access to all of the documents. That would be the best way. Of course, if you want to get onto eCIGRE, you can. It's ecigre.org. Even if you aren't a member, you can download any brochure that's over 3 years old. So all of this stuff that's referred to in SANS and that, you can get that without being a member. If you want to join working groups, that's really where you get a lot of the benefit. You can get that. You can join that. Prince Moyo is the chairman of the South African National Committee. He can advise as to where as to who the local members are. And for SEB2, it's Sharon Mushaba in Eskom, and she can assist in advising which working groups are set up and which you might wish to join. You don't have to attend all the meetings, or we don't fly anymore now anyway. A lot of them are done on remote, but the benefit is that you contact all the experts around the world on that topic. So you learn an enormous amount on a particular topic that you might be interested in. yeah, it's and or they could just email me if they have any further questions on that. But CIGRE always try to support the local institutes as well. So that's why we're giving the webinar through the SAIEE, which is great.
Dr. Stephen, thank you very, very much. If there are any questions, you can direct them through to the SAIEE or to Rob directly. And I would like to just thank you all for attending. We had a very, very high attendance today. We also, you can find up and coming webinars on the SAIEE webpage at www.saieee.org.za. So there is lots of exciting stuff that has happened. You can go and look at the previous presentations, and this one will be posted as mentioned before. And you can also go back and see some of the previous webinars that have been hosted. So to everyone, on behalf of the SAIEE and the KZN chapter, and a big thank you to Rob. Thank you very much, and have a good evening.
Thanks. Bye now.